Hi everyone, my name is Kuan. I'm a postdoc fellow at the University of Michigan, and I will move to UT Austin this fall. Today I'm going to talk about the role of mergers in the evolution of dark matter halos. This talk is based on 2 of my papers, and you're welcome to check them out. Here's the outline of this presentation. I will first give some background and the motivation for this work, and I'll explain how halo concentration evolves during and after mergers. I will then move on to halo anisotropy properties, which is the main part of this talk. I will close with conclusions and lay out future steps. So why do we care about dark matter halos? As cosmologists, we know there is 5 times more dark matter than baryonic matter, and halos contain most of the matter in the universe. Galaxies form and live in the potential wells of halos, and halos in turn dominate their formation and evolution. Halos are also natural labs for dark matter particle physics. Dark matter halos form hierarchically, meaning that smaller halos merge to form larger halos. This cartoon here illustrates the mass assembly history of a halo. We might naively expect that the properties of halos we see today depend on their mass assembly histories. Take halo concentration, for example. Halos are usually modeled with the N of W profile, which we know is wrong, but is still very useful for its simplicity. In the N of W profile, the scale radius Rs separates the inner denser profile and the outer profile. Halo concentration is defined as the ratio between the radius of the entire halo and the scale radius. The higher the concentration, the more matter there is at the center. The concentration parameter is widely used in the modeling of halo clustering, galaxy halo connection, lensing, and many other things. So here's what we previously knew about halo concentration. Earlier forming halos tend to have higher concentrations because they form their cores in the earlier, denser universe. However, this relation has a large scatter. This brings us to our motivation. Is there a way to define the formation time to quantify the mass assembly history that tells us all about the present-day concentration? This part of work used the dark sky simulations, which is a set of M-body simulations. In this figure, we explore the information content of different descriptions of the mass assembly history. We quantify the mass assembly history with M of A, the fraction of the present-day mass obtained by the halo at each epoch. The colored lines show the Spearman correlations between the mass fractions and the present-day concentration. Higher values mean more information, and the different colors correspond to different mass regimes. We can see that for each halo mass, a relatively broad range of intermediate epochs contain a significant amount of information on the present-day concentration, reaching correlation coefficients of about 0.7. However, 0.7 is not 1, and there is some information missing here. Next, we try to combine the different epochs and see if the combination has all the information we need. The horizontal dashed lines show the Spearman correlation from the best linear combination of the different epochs in the mass assembly history. We can see that we're able to reach about 0.8 with this treatment, which is nice, but not perfect, because 0.8 is still not 1. Now let's take a moment to summarize what we know by now. Earlier forming halos have higher concentrations. The intermediate stages of mass assembly history are the key stages, and any linear description of the mass assembly history has to lose information about the present-day concentration. So where does the remaining scatter come from? Where does the remaining information go? Let's examine the details of halo formation. In this figure, we show the evolution of one halo throughout its history. The top panel is the mass evolution, and the bottom panel is the concentration. You can see several sudden jumps in the mass and significant oscillations in the concentration. We also see that these happen around major mergers, marked by the vertical dashed lines. Major mergers are mergers that happen between halos with similar masses. One common choice of the mass ratio threshold is 1 to 3. When halos with similar masses merge, the entire halo is impacted. Now let's take a closer look at the major merger highlighted by the blue box. So here, the top row shows the trajectory of the smaller incoming halo with respect to the larger main halo in the three different projections. The bottom left panel shows the mass evolution, the bottom middle panel shows the concentration, and the bottom right panel shows the distance between the two halos, normalized by the main halo radius. You can see that the incoming halo enters the main halo, approaches the center, flies past it before turning back and spiraling in towards the center again. In the process, the incoming halo loses mass to the main halo, and the concentration of the main halo oscillates. When the secondary halo enters, it places a lot of mass on the outskirts of the main halo, which brings the concentration down. When it goes near the center, concentration rises again. When it goes past the center, concentration goes down again. And finally, when the incoming halo spirals back in and disrupts, concentration slowly recovers. In this case, however, this recovery is interrupted by another merger. So this cartoon here illustrates the process with three characteristic points in a merger: the incoming halo crossing the boundary of the main halo, the first pericenter, and the first epicenter. That was one merger that happened to one halo. So the different mergers all have the same dynamical processes. Go to the dark sky simulations and choose all the mergers that happen at certain times and stack each group. In this figure, the x-axis is time measured by scale factor A with respect to the time of measure. The y-axis is the evolution of the concentration normalized by the value at the time of measure. The different colored lines represent the stacked concentration evolution for measures that happen at different times. We find that different measures that happen at different times show the same ups and downs. But we can take this one step further. So mergers are dynamical processes, and it's reasonable to measure time in units of dynamical times when studying mergers. The dynamical timescale is defined as the time it takes for a test particle to orbit across a dynamical system. It depends on the mean density of the system, and fortunately for us, all halos at a given time have the same mean density. That's how they're defined. So cosmic time can be directly translated to the number of dynamical times. When we use this time unit, we find that the oscillations in the different measure samples all line up. So it's not just the qualitative behavior that's universal. The timescales in the measure-induced evolution are universal as well. However, does this matter at all? Is the measure response only a glitch in the entire concentration evolution, or is it actually significant? In this figure, we compare the evolution of the measure samples against a random sample throughout cosmic time. The black line is the random sample, which may or may not experience measures. We can see that the ups and downs in the measure samples have significant amplitudes compared to the range of secular evolution, and also last for a significant portion of the entire history. So we've shown that major measures really matter to halo concentrations, but major measures are relatively rare. A typical halo only goes through several major measures in its entire life. Minor measures, which happen between halos of very different masses, happen much more frequently. Repeat the analyses for minor measures and find that they too cause ups and downs in concentration, but with a weaker effect. So violent major measures and frequent minor measures together shape the concentration evolution of a halo. All right, let's take another moment to summarize our findings so far. Mergers cause dynamical responses in halo concentration. The responses have universal timescales and qualitative behaviors, which are significant and long-lasting compared to secular evolution. As a result, halo concentration cannot be trivially interpreted without accounting for the merger history. So where can we go from here? We used an M-body simulation. What if we go to a Hydra simulation instead? Can we look at other halo properties besides concentration? Can we also look at galaxy properties and how they co-evolve with halo properties? In the next part of the talk, we'll investigate a family of halo properties that measure the anisotropy state of the halo. This work uses the IllustrisTNG simulations. We use three criteria to define samples of mergers. the time of merger, the mass ratio, and the previous mass of the main halo. We will list these criteria for the measure samples we use in the following analysis. So this figure here shows the stacked radial orbit of the incoming halo with respect to the main halo. As a sanity check, we can already see the three characteristic points in this orbit: the crossing, the pericenter, and the epicenter. So anisotropy refers to the preference of certain directions over others. For example, a circle is isotropic and an ellipse is anisotropic. We look at four anisotropy properties. Halo spin, which is how fast a halo rotates, tells us about the environment and correlates with galaxy spin. Halo shape contains information of halo formation in the cosmic web, affects galaxy formation and evolution, and is important for modeling lensing. The position offset is the distance between the potential well, which is more robust to the ongoing measure, and the center of mass, which is more sensitive to the mass inflow. The velocity offset is the difference between the more robust core velocity and the more sensitive mean velocity. They're commonly used to measure the relaxedness of halos. So this is the main figure in our results. We use the same measure sample as before. The x-axis is time in units of dynamical times with respect to the time of measure. Each panel shows a different halo property. Besides the anisotropy properties, we also look at the halo mass and the rotation of the halo major axis. The measure sample is shown in blue, and the corresponding random sample, selected at the same time with the same previous mass, is shown in gray. The three characteristic stages of measure are marked with vertical dashed lines, and we measure the timescales associated with the peaks, troughs, and elbows in the property responses. You can see that the characteristic timescales differ between different properties. In the interest of time, we'll focus on two pairs of properties. So first, halo shape and position offset have exactly opposite responses. For C2A, the halo shape, lower values mean more elongated and less spherical. As the incoming halo crosses the boundary, the halo becomes more elongated, as it now has two major density peaks that are apart from each other. Towards the pericenter, the halo becomes more spherical. Towards the epicenter, more elongated. Spiraling back in, more spherical. So the opposite happens for the distance between the two measures of halo position. We see that the first peak and second trough in C2A halo shape happen a little earlier than the times of the pericenter and epicenter, and that's because the incoming halo is losing mass, and there's a trade-off, a sweet spot between its position and its remaining mass. And second, we'll look at the position and velocity offsets together. Very roughly speaking, the position offset represents the potential energy of the system, and the velocity offsets represents the kinetic energy of the system. At first, both grow as new energy is brought in by the incoming halo. Then one of them increases as the other decreases when the two forms of energy transform into each other. However, energy is not really conserved in the system, and both start to decrease as the energy dissipates. Now let's draw some conclusions. So in short, halo properties dynamically respond to measures. The response is significant, and each property has its own universal behavior with universal timescales, which are different between different properties. And in the future, we'll look into galaxy properties as well as halo properties, which will tell us about the coevolution of galaxies and halos. One possible future step is to examine the dynamical details of mergers, such as the impact parameter, the encounter velocity, etc. We can also connect this to the cosmic web, which determines which halos merge with one another. Some of the broader implications involve the local group, where we can use our findings to help reconstruct the recent merger history and the satellite kinematics. Our findings can also be applied to galaxy clusters, where we can explore observational proxies of the dynamical history of these galaxy clusters. So thanks for listening, and I'm happy to take questions and discuss possible applications of this work. Thank you.